Hi, this is Paul, the SDR guy, and in today's video we're going to learn about single sideband modulation. We're going to look at both upper and lower sideband. We're going to be using GNU radio and an RTL-SDR. I'd like to thank Gary Schafer for assisting me with this video. Gary, a big shout out to you. Thank you so much. Let's next take a look at a preview of what we're going to be doing and learning about today.
November 9, November Tango Charlie, thanks for your patience, your 5-9, row it down. November 9, November Tango Charlie, thanks for your patience, your 5-9, row it down.
Let's take a look at what amplitude modulation is. Well, we start out with a message signal. You can envision this as being someone speaking or music playing. And then we have a carrier signal, and these two signals are combined, and this is what you see down here in this combined signal row. Now, one of the things I want you to notice that the amplitude here rises and falls, and then rises and falls just like the message signal. And then I want you to also notice that the mirror image of that message signal is on this bottom half here. And this is the same information. In a 100% modulated AM signal, the power distribution is 2/3 is in the carrier, and we need to remind ourselves that there's no information in the carrier. And what remains is 1/6 in the lower sideband and 1/6 in the upper sideband. In amplitude modulation, information content is redundant between upper and lower sideband. The spectrum is a mirror, and either is sufficient. During this video, we're going to start speaking about I and Q signals. So what we want to do is to introduce you to what that means. Here we're plotting out a cosine wave, and notice here at 0 it starts at a value of 1, then repeats here as you see in the dashed lines. And then we're plotting a sine wave, and that's in the solid blue here. So we will be referring to these signals as I and Q, and the Q just stands for quadrature, and it means that there's a 90-degree phase shift. Okay, so let's put together a little example using GNU radio that will show you how we can create quadrature signals. So notice here we have two signal sources. We have a cosine and we have a sine. They're both 10 Hertz. And anytime we're creating a flow graph, when we don't actually have hardware included, it's always best practice to put a throttle in there somewhere. At any rate, the output of both of these are going into a time sink. And this is what you would expect to see if you were using an oscilloscope. So let's go ahead and run the flow graph. And here you go. The blue is the cosine signal. You can see the legend there. It starts out at time 0 as being a 1. And then the sine signal, it starts at 0 at time 0. So there you have that. Up to this point in time, we've been laying the framework, talking about single sideband. So the next thing we're going to do is we're going to look at an upper sideband transmitter that's implemented using GNU radio. Here, we're looking at a flow graph of an upper sideband transmitter. Before we delve into the details of this, let's go over and look at a website. And as I often say in my videos, I'll be including all the links to all the resources that we speak about in today's video. So in the first part of the video, I mentioned a gentleman by the name of Gary Schafer that provided a great deal of assistance to me in putting this particular video together. And in addition to it being a learning exercise for me, it also served the same purpose for Gary. So Gary has written what I consider to be the most approachable, in other words, the most understandable blog post on understanding single sideband and using GNU radio. So this is a really good read. You might want to read it a few times. There's so much meat in this particular video. So let's break this particular flow graph down. So we have a wave file source, and I've simply created a little test audio file. And I have this set up to repeat, and the output of this goes into a bandpass filter where we're passing frequencies that are greater than 300 hertz and less than or equal to 4 kilohertz. The next thing that we're going to do is we're going to take the output of that and we're going to go into a Hilbert transport box. Well, you're probably scratching your head and saying, well, what in the world is a Hilbert transform? Well, let's go take a look. So if we go to the GNU radio explanation, it says that that basically it does a 90-degree phase shift. But it actually is doing more than that for us. And so to get a understandable definition, I brought up my good friend, the ChatGPT app, and my question was, in simple terms, what does the Hilbert transform do? The response, in simple terms, the Hilbert transform takes a signal and shifts all its frequency components by 90 degrees. Here's the intuition. Imagine your signal is a combination of many sine waves at different frequencies. The Hilbert transform changes each sine wave into a cosine wave and vice versa without altering the amplitudes. The result is a phase shifted version of the original signal. Well, why does this matter? Well, if you combine the original signal with its Hilbert transform, you can make a complex valued signal whose real part, I'm sorry we're having to get into imaginary numbers here for a bit, is the original signal, and the imaginary part is the transformed one. And this has a special name. It's called an analytic signal. And this analytic signal is handy for finding the instantaneous amplitude and phase of a signal. And this is often used in communication, in modulation, and signal analysis. So now that we understand, or have a basic understanding of the Hilbert transform, the output of this goes into a fast multiply by a constant block. And once again, let's bring up GNU radio. And as you're learning more about signal processing and GNU radio, you can actually make little flow graphs that help you understand what function a particular GNU radio block performs. So I've put together a simple little example here that will show us what a fast multiply block does. So we're using an input of, in this case, a sine wave, amplitude 1, it's 1 kilohertz, and we're going to look at that with a time sync. And then we're going to route the output of this also to the fast multiply block and take a look at that. So let's go ahead and run the flow graph. And notice after the signal source, the amplitude varies between +1 and -1. However, the fast multiply block multiplies that signal by 2, and so therefore we have an amplitude of 2 to -2. So that, quite simply, is what the fast multiply block does. It does the multiply, and it does it very fast. So let's go ahead and close this down. Let's go back to our upper sideband transmitter. And the output of the fast multiply is routed this direction. And at the end of the day, we're using our PC sound card, and it is set to basically play 48 kilohertz audio. Well, the output of the fast multiply is a complex number, and we've got to convert that into a real number. That's what this box does. And then this multiply constant here, this is being multiplied by a very small amount. It's 510 to the -3rd. And this serves as a volume control. And then we're routing that to an audio sync. And we're going to also take a look at this signal in a time sync. So let's go ahead and run this flow graph.
This is a test audio file that is being used with the RF line transmitter. This is a test audio file that is being used with the RF line transmitter. This is a test audio file.
So I'm going to turn the volume down here. So this is our first actual look at a upper sideband signal. So 0 would be where you are tuned to, if you will, on a real radio, and then the signal basically is on the right half. And the other thing that you want to note here is that there's no carrier. So all the information and such is contained within the upper sideband. And as we said earlier in the presentation, this is 1/6 of the power when compared to an AM signal. And we're also looking at the audio down here. And so here you have the example of an upper sideband transmitter. Well, since we are using an RTL-SDR, it cannot transmit, so we're having to simulate that, and that's why I used a wave file source. The next thing we're going to look at is we're going to take a look at a lower sideband transmitter. And this explanation will go much quicker because everything is the same except after the Hilbert transform, we're running this through a complex conjugate. Well, again, we're talking about imaginary numbers, so let's take a look at that. And in mathematics, the complex conjugate of a complex number is the number with an equal real part and an imaginary part equal in magnitude but opposite in sign. And that is what the complex conjugate does. So let's go ahead and run this. I have the audio turned off. It's playing the exact same file. So let's go ahead and run the flow graph. And here you go. Once again, here's 0. And this again is frequency that you would be tuned to in a real radio. And then the sideband is below that frequency, hence the name lower sideband. We're now going to look at a GNU radio flow graph that implements the Weaver method to demodulate an upper sideband file. You'll notice straight away that there's a considerable amount of complexity in this flow graph relative to others that we've shown so far in our beginner series. But let's refer you once again, let's come back to our web browser and Gary Schafer's most excellent blog article where he describes in detail of how this Weaver method is used to demodulate the sideband signals. There are a few things I'd like to call your attention to. One is we're using a source here that is different than what we've used in earlier videos. In this particular case, we've used the open software package called SDR++, and we have recorded a IQ file of some ham radio HF transmissions. And well, why did I do that? many of you will not have antennas that are sufficient to pick up ham radio HF signals. So this is in the place of that. There's a few things that I want to point out, and I'm not going to go into excruciating detail. As I said earlier, I'm going to refer you to Gary Schafer to explain the details of how all of this works together. But I do want to point out a few things. So let's jump back over to our web browser. And within GNU Radio, there's this block that's called a frequency translating for filter. And the basic idea of what this thing does can be illustrated in pictures. Let's say this orange block here is what you want to listen to. Well, this translating filter will move this block over to what they call baseband at zero hertz, or sometimes referred to as DC. And then they will use a filter, and then your signal of interest is as shown here. So within GNU Radio, there's this idea of hierarchical blocks. These are blocks that implement the functionality of, two or more lower level blocks, if you will. And one of these that I want you to look at is a rotator block. And you can visit this page, you can implement this and experiment with it. And the thing that you will notice about this, it's going to be used to translate or move the frequency that it's tuned to baseband. And when we look at the next flow graph, we're going to also be seeing this particular feature implemented that's called Zoom FFT. And that came from ideas presented in a book by Richard Lyons, and this is a really good book that you may want to consider investing in. Richard Lyons has made many, many valuable contributions to the field of digital signal processing. So let's head back on over to our flow graph. And I'm basically going to, here's a rotator that's used, and here's a rational resampler, and decimate is going to be cutting the sample rate down, and ultimately we're going to be reducing this so that it can be the end result listened to on your PC sound card. But let's go ahead and move this over to the right here, and notice this is a Zoom spectrum, and we're sending the output of this into a virtual sync. So let's scroll down and let's scroll back over to the left. Here's our virtual sync. We're doing some frequency translation again. And again, for the details of how all of this works, check out Gary Schafer's webpage. And ultimately, we will go to an audio sync. So let's go ahead and start this flow graph up.
November 9, November Tango Charlie, thanks for your patience, your 5-9 Roatan. November 9, November Tango Charlie, thanks for your patience, your 5-9 Roatan. November 9, November Tango Charlie, thanks for your patience, your 5-9 Roatan. November 9, November Tango Charlie, thanks for your patience, your 5-9 Roatan.
The other thing that I wanted to make you aware of is in this RF spectrum, we're looking at the full spectrum, and when we use the zoom spectrum, let me go turn this off. When we use the zoom spectrum, then we're able to zoom in as shown in the diagram that you're looking at here. So once again, this particular flowgram implements the Weaver method to demodulate an upper sideband signal. The very last thing that we're going to do in today's video is we're going to look at using an actual real RTL-SDR, and we're going to connect this to an antenna, and we're going to be able to use this to find and listen to single sideband transmissions that's in the amateur radio band, and you're going to be able to listen to both upper and lower sideband transmissions. What we want to do next is we want to show you how to use the user interface for this particular flow graph. So I have my RTL-SDR plugged in. There's no antenna, and that will be okay because I'm just wanting to show you how to use the user interface. So let's go ahead and start up our flow graph. And what I want you to notice here is this is set up for listening to amateur radio on 80 meters all the way up to 10 meters. And this will be with your RTL-SDR, but you do need to have an antenna that will allow you to receive this. Notice here, sideband, we have upper, and you can click on the drop down and get lower. The RF gain and the IF gain will control those respective gains. On the RTL-SDR, there's volume, and then down here there's 3 tabs, one of which is the zoom waterfall, and there's no signals to display right now. And then the next one here, gain adjust, this is very important. So when you're setting your RF gain and or IF gain, you want to make sure that this does not clip. You basically want the gain to be loud as loud as it can get without clipping. And then back here is the original page, if you will, and here where the red is, we're tuned down to the lower end of the band, the voice part of the band, and this has us zoomed in. Lastly, this is audio, and you can similarly adjust the volume so that it can be as loud as it can get without clipping here, and that means going above +1 or -1. And the very last video segment we will be showing today will be me actually plugged in to an HF antenna and listening to some ham radio operators.
Yeah, have a good one, Alan. Good to hear you again tonight. WA1NIP. And thanks, Jeff. 73, Mark. Thanks, Jeff.
Oh, it is absolutely good to hear you out here, Mark. And we're going to try and get on here a little bit more often, but boy, right now the schedule just is nuts. So I look forward to this. This is kind of my relaxed time. So let's see, clear with Mark, and say hello to Tim in Ohio, K8WBL, 73 round there, Tim.
Hey, Alan.
Yeah, good.
I wanted to tell you, you look great on the boat, by the way. That was a great picture, so don't be embarrassed.
Oh, if I had about 25 or 30 pounds less, it would have been even better, but thank you.
At least you were out there doing it. All right, back to you, sir.
All right, thanks. I'll say clear with you. Let's see if Frank is still out there. KB2CWN. Frank, 73 round, Frank.
I'll get him. All right. KB2, Charlie Whiskey Nancy, 73, Frank.
Once again, this is Paul, the SDR guy. Thank you for watching. Please consider liking the video and subscribing to the channel. And also feel free to make suggestions in the video comments on subjects that you would like to see me cover in future SDR videos. So with that, have a great day.